Okay, Organic Chemistry 2330. We're going to continue on with our chapter 15, enolate ions. We're going to do additional reactions. In the last one, we learned about the aldol reaction. In this one, we're going to learn about a different reaction called the Claisen. Okay. In the Claisen condensation, we have it a little bit different than before. In the aldol condensation, we took either an aldehyde or a ketone that had beta hydrogens on it, and we deprotonated it to make our enolate ion. In the case of the Claisen condensation, it's the same thing, but instead of using an aldehyde or a ketone, we're going to use an ester with alpha hydrogens, okay? So what we're gonna do, and from the product of that, we're gonna end up making what we call a beta keto ester. Notice this little thing did not come up. It's a beta keto ester. So remember, our alpha carbon is the carbon next to the carbonyl. That means our beta carbon is one more carbon over. Therefore, we have like a 1,3-dicarbonyl compound from the product of this. Okay. So looking at that right here, the way we start this is we take an equivalent of our ester that we have. And remember, it has to have some alpha hydrogens on it so we can make our enolate. We deprotonate this. Typically, we don't use water in this reaction because we don't want to hydrolyze off our ester, okay? So we typically would use an alkoxide or a salt of an alcohol in an alcohol so that it doesn't happen. And we typically use the same salt that we have the ester made. So if we have an ethyl ester, we're going to use an ethanol salt. If we have a methyl ester, we're going to use a methanol salt. The second step of the reaction is adding acid to the system, which will liberate our free alcohol and our beta keto ester. Okay, so a little bit more about that. So we have our portion here, which came from one of our equivalents, and then we have our part right here. This is the part that formed the enolate and attacked our system. Okay, let's go and look at that beta keto ester name again right here. This is the ester we started with on our, that we're going to form our enolate out of. This is the carbon that was on that ester, and this is the other half of that ester group where we've displaced off an OR group, okay? So because we have this ketone on the beta carbon and we still have our ester, we have a beta keto ester, okay? So in the Claisen condensation, what we're going to do here is we're going to take two of the same molecule and join them together and lose ethanol. Okay, notice that these are exactly the same compound, just drawn two different ways. Okay, the reason we're drawing that is that we're going to form the enolate on this compound here, and then this enolate is going to attack this carbonyl and kick out this ethanol group here to generate our ethanol as our final product and our beta keto compound, okay? So again, like I said, this requires non-water. When we actually do the reaction, we use water to work it up. We don't want to clip off the ester too early. At the end of the reaction, we can, but we don't want to do it yet. Okay, so let's look at the mechanism. So the first step in the mechanism is the same as with making any enolate, is we remove a proton from an alpha carbon. Okay, so in this case here, we're going to use the ethoxide to remove this proton that again is in the alpha carbon next to this carbonyl. Okay, so that's going to generate our resonance stabilized enolate ion. Okay, now that we have this resonance stabilized enolate ion, this carbon can act as a nucleophile and attack another one of the carbonyl compounds that is already in solution. When it does this, it forms our new carbon-carbon bond and gives us this tetrahedral center right here, where we have this alkoxide ion plus this ether on this side here. So the next step in the mechanism is actually for it to collapse or lose the alkoxide ion by having the electrons come in from the oxygen up here, kicking in to give us a carbonyl compound, these electrons kicking out to give us our free alkoxide ion. Notice we started with an alkoxide ion that deprotonate to make our enolate. We're regenerating our alkoxide ion at the end here. Okay, so once that leaves, we now have our ketone compound here from the ester we attacked, and we still have our original ester from our original enolate, okay? Now, the next thing that happens that makes this reaction so interesting is the fact that this is a strong enough base to pull the proton off in between these two carbonyl compounds right here, because this proton is now more acidic than it was for the original compound. Now, this serves two purposes. Number one, it generates this anion here. This anion is nice and stable and does not react further. So until that reaction will sit here around with this beta keto ester, will just sit there until you acidify the reaction at the end, and it will not react further. Like the aldol condensation, it can do additional products. This one stops because of the stabilized anion. Okay. So the last step is at the end, when we add water or acid, it'll protonate this thing, giving us our beta keto ester compound. Okay. Now, just like when we had the crossed aldol, the intramolecular aldol condensation, we can also do an intramolecular Claisen reaction. And when we do the intramolecular Claisen reaction, we call it the Dieckmann condensation, okay? Just like with the intramolecular aldol condensation, you can form 5- and 6-membered rings only. If you deprotonate and can only form a 4-membered or a 7-membered ring, it will not progress, okay? So, using what we know from the intramolecular aldol condensation, we again can form that 5- and 6-membered ring, but it undergoes the exact same mechanism of our Claisen reaction. We form our enolate attacks, we lose an alkoxide, we generate an anion that is stable until we quench the reaction, and then we end up with our beta keto ester compound. Okay, so how do we do a successful cross-Claisen reaction? Just like in the aldol reaction, we are looking for one of the substrates to have alpha protons, and in the cross-Claisen, we need the second ester to not have alpha protons, just like in the aldol. So if we look at our substrates here, we take, if this side is the ester of formic acid, so we have ethyl formate, so there's no alpha hydrogens here. In this case here, we have a diester of carbonic acid, and we call that diethyl carbonate. Here we have the diethyl of a diacid, the diethyl ester of a diacid. So in this case, we also have no alpha hydrogens, and if we have the ester of a benzene right here, we have no alpha hydrogens. So, just like in the cross aldol, no alpha hydrogen leads to a cross-Claisen condensation, but it generates some of the same products. So let's look at the products of this right here. So again, we have our compound with no alpha hydrogens. We have our ester with alpha hydrogens. Therefore, we're going to generate our enolate ion on this position where we generate that. We're going to have it attack the carbonyl. This methoxide is going to leave, and when we protonate the reaction at the end, we'll end up with methanol and our beta diester compound. Our beta keto ester compound. Okay, and again, it works really cleanly because we only can form one compound, can form the enolate, the other compound cannot, and therefore it will react specifically to give us a single product. Okay, just like in other, from previous reactions, we know that we can hydrolyze esters, and we can hydrolyze esters with either acid or base to generate a carboxylic acid. Once we generate that carboxylic acid and we have a beta keto compound there, what can happen is that we can actually do what we call a decarbonylation reaction, which means we can lose the carboxylic acid portion that was part of the ester off of the reaction. So let's take a look at what that means. Okay, so in our original Claisen reaction, we took this right here, this ester right here. We deprotonated here. It attacked another one of it to give it our extended new beta carbonyl compound. So this is our beta keto ester. Now, if we take this compound here and then hydrolyze off of this to generate our OH group right here, we're going to end up with our ketone carboxylic acid product. Okay, so what that looks like is something like this right here, where now we have our ketone that we got from our addition of our enolate. We've now taken off our ester and we have our carboxylic acid. Now, what can happen when we heat this with a little bit of acid, what can happen is this OH group can come off as CO2, okay? Now, but I wanna show you one extra step here to show you why it works, okay? So if we rearrange this compound to have the hydrogen here and the carbonyl here, and there's only one bond between there, okay? Now, what it can form is this six-membered ring, okay? This is the key step in this decarbonylation reaction, is forming this six-membered ring. Because once we form this six-membered ring, what can happen is that we can have one of the lone pairs from up here reach out and grab this hydrogen. These electrons kick in, giving us our other compound. These electrons kick here, and when that happens, it loses CO2 and gives us our enol form, and then our enol form will reconvert to our ketone form. So the whole reason you can get a beta carbonyl acid to decarbonylate is you form this six-membered intermediate here. Once you form that six-membered, it makes it very easy to lose CO2 and leave with your final product as a ketone or a carboxylic acid. Okay, so that being said, let's do one little kind of reaction here where we look at the result of a clase condensation. We want to see how we can convert this compound over and how we can synthesize this compound. So the first thing we want to probably do is we want to make it into an ester. And